So our speaker today is named Francois. He'll be speaking about the climates of planet Mars. And our speaker received his PhD in physics from the University of Paris, where he also got a master's degree in oceanography and meteorology. So you can see he has a varied background. He is currently a senior research scientist at the Laboratoire de Météorologie Dynamique at Paris in France. And he previously was a scientist at the NASA Ames Research Center, so we're glad to welcome Francois back out here to California. He managed to sneak out of a workshop to come and give this talk, so we're very pleased that he's here. And just another interesting note is that Francois is also the author of an award-winning book called Planet Mars, Story of Another World. So today he'll be speaking about the climates of planet Mars. Let's welcome our speaker.
Good afternoon. Thank you very much for coming. It's really a pleasure to be here in California and at SETI, where I know lots of people. So today I'm going to talk about planet Mars. Initially, Adrian told me that there will be a mix of scientists and non-specialists. So I started with this is Mars, a small planet very close to the Earth, not that close. But so I just this picture used to remind you that Mars is a kind of small Earth with a thin atmosphere, but except for that, it's really like a desert planet. The length of the day, as you know, is 24 hours, 40 minutes. The obliquity is about the same, so the seasonal cycle is about the same. So there's a lot of similarities. But just like the Earth's climate is made complex by the presence of the oceans, of the atmosphere, of the clouds, of the ice, and so on, Mars also is a complex climate system. Today I won't tell you about all the detail of the climate system. Could spend several days doing that. You have this system with the atmospheric circulation coupled with the dust cycle. It's a desert planet, so dust is very important. The CO2 cycle, the atmosphere can freeze in the polar caps and seasonally and even permanently at the South Pole. And also a very peculiar water cycle. And this is what I'm going to talk about mostly today is really about the water cycle of Mars. So for those of you who are not that familiar with Mars, we'll start with a few reminders. Everything related to water cycle and present-day Mars is really connected to this little spot at the top here at the North Pole. North Pole, you have this relatively fresh and pure water ice layer interacting with the atmosphere. Of course, this is covering a very massive polar cap, the polar layer deposits. But what is really important for our discussion today about the present-day climate is this fresh layer of ice, which is covering this area. It's about 1,000 kilometers in diameter. And this is really where the ice, the reservoir ice connected to the atmosphere is. So when you want to understand the water cycle on Mars, you just have to understand that this is where the ice is stable and remains, and everything then is logical. Typically, this is just a zoom on this ice layer. Typically what happens is that during summer, so in summer, this ice is exposed to the sun, it warms, it sublimes, and then the atmosphere will transport the water vapor to the other latitudes. It's not much water vapor, but it can nevertheless condense and form clouds and comets. More quantitatively, this is a picture showing the typical water cycle for the water vapor. What you see here is a graph where you have latitude as a function of season on Mars. You can see that it's the Episodic, so solar longitude. And you can recognize here that you have, in summer, a maximum, the emission of water vapor. And then you can see the transport of the water vapor into the atmosphere, to the equator, with a little maximum also when the seasonal polar cap in the south is subliming. In white is where you have no data. And this is really telling us about the water vapor. So you can see here the unit is precipitable micron. If you take the entire amount of water vapor in the atmosphere, you put it on the ground. The maximum here is like 50 microns. It's not much water, of course. Nevertheless, because Mars is a very cold planet, it's cold enough so that you can condense and form clouds. This is one of the most famous pictures from Viking a long time ago. You can also form frost, another picture from Viking. Frost on the surface, during winter, typically, just like in the mid-latitude of the Earth. And this is what you can learn. So to learn more about the water cycle, what has really been very useful, to really better understand the climate of Mars, and in particular the water cycle, what we have done is to simulate the climate of Mars using global climate models or general circulation models. So these models are developed in various teams. The pioneer team in the world was actually Danza Ames here, and we also have our own program with developing this model. So this kind of model is quite ambitious, in fact. The goal is to simulate the reality using only universal equations, but our goal is to have a complete model that predicts all the available observations, and we have a kind of virtual Mars in our computer. And using that, it's a good tool to investigate what's going on the planet. So to give you an example, just to show you, when you put the right equation, fluid dynamics, relative transfer, you read the atmosphere, everything rotates, and you can quite well predict and reproduce the observations. For instance, this is the zonal mean temperature on Mars at a given season, at the end of fall, of winter, northern winter. And you can see the plot, the model, the prediction from our global climate model, and below the observations from Mars Global Surveyor. And I can go around with this very simple comparison. I can go around with season, and it's a movie with my finger, and you can see that the model can predict a lot of detail, the methodology, the waves. Can not really see it here, but all the variability connected to the season and so on. And once you have that, so once you have a good model that predicts not too badly the temperature, the circulation, we found that it's not too difficult to simulate the water cycle on Mars. You just put a few equations, a few lines of Fortran, literally, and you put the equation to account for the sublimation from the ice which could be on the ground, particularly the North Pole. Then you mix and transport this water vapor in the turbulence in the layer, the convection, the general circulation. And then you account for the fact that it's very cold, you can condense and form clouds on condensation on the surface. A few equations, not too complex, a few unknown parameters that you can tune, and once you do that, we find that it's not too difficult to reproduce what has been observed. You can see here on the top the observations. Where it's white again, you have no observation. And below the model prediction, once it's a little tune, of course. And you can see we reproduce quite well, and that means we more or less understand the basic rule to first order that govern this water cycle. With this maximum, you can see the red point, this is northern summer again, and then you transport the water vapor. If you want to improve the comparison, I can put the same mask to reproduce the fact that there is no observation during especially winter and the polar night, and you can really feel the match is okay. Similarly, you can do the same thing with the clouds. This is a seasonal cycle of the clouds, once again, altitude and season. You can see there is a very marked seasonal cycle with the clouds. In the same, with a season you can see during northern spring and summer, where you have thick clouds in the tropics. All year long, around the polar night, you can see what we call the polar hood. And the model, not only our model, models in general of Mars can do a very good job to reproduce all these observations. So we have the feeling that we understand more or less quite well the behavior of water on Mars. What we've learned from this, just one more thing I forgot to say, is that we also can simulate the behavior of the surface water ice, the frost that I told you. I don't have detailed comparison. I can just, for instance, show you that such a model predicted quite well the behavior of the frost that was observed by Viking at 48 degrees north. And but what we've learned from this as well is that the ice never accumulates anywhere. It's only stable at the pole and never accumulates anywhere. And so I can summarize here what we've learned from this kind of modeling. First, again, that the surface water ice cannot accumulate outside the polar regions. It's unstable, can stay a few weeks, a few months, but when summer comes, very hot, very warm for Mars, and then it sublimes and only accumulates at the North Pole. In other words, that's the point 2, this is a closed water cycle. Whatever sublimes during summer at the North Pole, transported in the atmosphere, and can freeze in some location, but in the end go back to the North Pole. There is no other thing except maybe for those who are familiar with that, there is a small residual cat of CO2 ice at the South Pole where there is a little cold trap there. It's not very important thing. So it's a closed cycle. The water which is in the system is always the same, going back and forth from the North Pole. And finally, just a point which is important, there is no, as far as we can tell, no liquid water possible on the surface. The pressure is too low. So sometime you can be above the triple point, above 0 degrees Celsius, but the pressure is so low that every droplet of water that could form then will evaporate very quickly. And in any case, when we do simulate that, if you put ice somewhere and you raise the temperature, for instance, you put it in the night and you raise the temperature in the day, it will sublimate well before you reach 0 degrees Celsius. So the water, liquid water, will be extremely unstable. I'm sure you all know that. So these are the things that you can learn from these models and from analyzing the observations. However, so Mars is a very dry planet, very dry surface at least. But of course, so that's the present day climate. Of course, as you all know, the interest of Mars is not only on the present day climate, which is interesting, nevertheless, but it's also the past climates, and that's what I'm going to talk now. This is a geological map, topography map of Mars, and you can see very rich geology with lots of craters, of course, volcanism, and so on. You all know that. What's interesting is that the years and years of analysis of the geomorphology of Mars have taught us a lot of information about the past of the planet and have demonstrated that the climate was different in the past. In particular, we can separate two eras. The first is what the era that's called Amazonian, which is the recent Mars. Recent Mars can be 2.5 billion years old. It's okay, that's recent for Mars. And then in the old terrains, the terrain which is actually here very much cratered, you know that when it's cratered that means it's ancient, then you have an ancient Mars. And the geological records, probably many of you know, that it tells us that in the ancient Mars you have clues about the fact that there were lakes, rivers, liquid water activity. And also, for the recent Mars, you have clues that it has not always been this dry surface where nothing happened. Something happened related more to ice. And I will now talk about this recent period, the Amazonian, where probably much more ice was involved in the system. And in fact, I will give you a few information about how we have learned that ice was probably involved in the climate of Mars in the recent past, a few hundreds of thousands, a few million years ago on the planet. The thing is that below this surface, which seems to be dry, we have discovered lots of places where there is in fact ice. Again, ice is not stable on the surface, but it can be stable in the subsurface. Among the first demonstration that we have did thanks to the nuclear physics, the neutron spectrometers, the instrument, the gamma ray spectrometer, which included a neutron spectrometer about the Mars Odyssey, 2001 and 2002 and so on, which was designed to detect the presence of hydrogen in the subsurface using the flux of neutrons. You know, you have cosmic rays all the time hitting the planet, and many neutrons are ejected, and then, depending on the amount of hydrogen, in other words, of water which is in the surface, they are slow. This was designed to measure the presence of possible ice in the polar region and stuff like that, and people were expecting to see ice in the pores. But what was surprising is that Mars Odyssey not only detected ice in the pores of the subsurface, it actually detected a layer of almost pure ice covering a large part of the planet. This is another slide. Okay, you may have seen that before. This is a map from the Mars Odyssey team showing in blue, in dark blue here, the area where just below according to their measurements, just below a few centimeters of dry sand, they should be protected then from the evaporation, the instability of the surface that I mentioned to you. There should be a layer of pure ice, and that was unexpected. It was so unexpected, and when this discovery was made, it was the time of the selection of the new SCAP mission on Mars, and it was decided to send a spacecraft to check on site at this location if it was really true that there will be ice, and understand the nature and the characteristic of this ice. So Phoenix was sent there, landed on May 25th, 2008, and it was a lot of excitement for people who were interested in this kind of subject to see what Phoenix will see, what will be the first ground view of the Mars polar region, and there were no surprise. The landscape was typically polar. Well, that's a joke from Peter Smith, the PI of the project. Well, it was actually typically polar, because you can see here the structure on the ground. These are polygonal terrains, what we call polygonal terrains, which are characteristic of a surface where you have ice in the subsurface, and very ice-rich. For instance, this is an example what you see in the famous dry valley in Antarctica, which are kind of Earth analogs of Mars, and you can see very well this polygonal structure on the surface. To be honest, it was known before. There have been a lot of geomorphology studies of this polygonal structure, but which already demonstrated that there will be a lot of ice there. But it was surprising to see that much ice. And in fact, Phoenix quickly find that there is indeed ice below a few centimeters of dry sand and dry sediments. You really have ice. You may remember this picture, which shows that the ice was exposed by the landing structures. And even more, Phoenix digs some trenches, and in particular in this, on the left, they got fine ice outcrops, which are 99% pure ice, very dry, pure ice. And it's quite interesting to understand the origin of this ice. But outside these mid-latitude regions, where in some way subsurface ice was expected to be stable, there have been other discoveries in the past years. Lots of work has been done by various teams, especially at Brown University with the team of Professor Jim Head. They have discovered many kind of in these clues about glacial features, glacier, rock glacier, moraines, whatever, in many locations. Not everywhere. You can see here a kind of map at the mid-latitudes. You can see, this is for instance the famous place called Deuterius Mansei, where you have lots of what is called low-bed debris aprons, which are kind of marsh glaciers. Since then, recently radar measurements have demonstrated that you have many of these features here are full of ice. That's another example in Eastern Hellas, where you have plenty of glacier-related features. For instance, you can see here this moraine system surrounding a kind of glacier. That's a place which is dear to Bill Hartman. And even into the tropics, where ice should be absolutely unstable, the geomorphologists have discovered a lot of clues about past glaciers, especially on the western side of the big mountains. This is a Tarsis area. You can see the Olympus Mons, Asclepius Mons, Tagonis, and Arcia. And there, on the eastern, western side of this glacier, there is this area here in yellow, which had been kind of mystery since the Viking era. And following a pioneer work by Babel Luket, the head, Jim Head and colleagues demonstrated that this area yellow is characterized by the presence of moraines, of remnants of glacial feature. That's surprising. Ice is absolutely unstable in this area right now. It will sublime really quickly. So what happened? Well, there have been different scenarios. For instance, especially for the mantling, there is a suggestion that maybe it's just the diffusion of water vapor into the subsurface. It's a process that can also happen on the Earth, that can fill the pores and make the ice, but such ice-rich layer is kind of mystery. For the volcanic glacier, typically, some team had suggested that it was probably the interaction of a volcanic activity with deep ice or deep water that forms, that will create kind of hydrothermalism, and all this will freeze and make glaciers. And of course, there is a third scenario, which will suggest that maybe that was just a glacier that were made like on the Earth with snow, but under a different climate. And of course, I'm a climatologist, planetary climatologist, and we got interested in this third situation. Maybe we should study the past climates. And indeed, we expect that the climate could have varied on Mars. And the reason is like on the Earth, is because of the change in the orbit and the rotation parameters. Probably know that, for instance, the Earth orbital parameters, and particularly obliquity, slightly vary. The variations are quite limited, between plus or minus 1.3 degrees typically. And this is enough to trigger the ice ages, along with the variation in the perihelion and date and so on. to trigger ice ages on Mars and lots of climate change related to the Milankovitch cycle. And for a few about 20 or a little more years, we have discovered that Mars is not like the Earth. Thus, the obliquity does not vary by only plus or minus 1.3 degrees, but it can vary hugely between 0 and more than 60 degrees. So we could expect huge climate variation due to this change. This is, for instance, a plot showing you the variation of the obliquity on Mars between minus 10 million years and 0. And you can see that not that long ago, the obliquity could go as high at 35 degrees and as low as 15 degrees. And more than 5 million years ago, it could go all the way up to 45 degrees, which is really high. So it was compelling to study what could happen on this planet. Can we imagine what is the Mars water cycle at high obliquity? And of course we can, because we have the model that I just described to you, which works very well for present-day Mars. And it was very easy just to take this model, change one number, typically the obliquity, and see what happened. See what happened, we can guess. We can, as I remember that the water cycle is really controlled by the insolation of the North Pole. In summer, if you are at high obliquity, of course the North Pole is even tilted more toward the sun, so you have more sublimation, and you can expect an enhanced water cycle. And indeed, that's what the GCM will suggest. You can see here again the same plot showing the water cycle with latitude and season. At the top, it's on present-day Mars. You recognize the value here: maximum 50 precipitable micron around the pole, and on average 10 precipitable micron, not much. And if you do the same simulation just by changing one number, put the 45 degrees, then you can see thousands of microns above the polar cap, and typically 10s, 20s, 100 precipitable microns, so 2, 3, 5 more water vapor in the system than on present-day Mars. So when we do this experiment, it's interesting because if you increase, for instance, the obliquity from 25, which is the present-day obliquity, to 30 degrees, a little more, you find that you have the same kind of planet. In other words, you have a water cycle, more water vapor, more clouds, but the ice is still not stable anywhere else than on the pole. So all the ice which is sublime during summer goes back to the pole. The same at 35 degrees, 40 degrees and above, and we discovered that somewhere above 40 degrees obliquity, the ice is no more stable at the pole. Really, the heating is too strong, and the ice will accumulate somewhere else. And what we discovered, using our climate model, our weather model, is that the ice will accumulate in very specific regions. This is what we obtained. This is a simulation performed at obliquity 45 degrees with high resolution, so that we are sensitive to topography. And we discovered that the ice tends to accumulate on the western flank of the volcanoes here. And of course, remember the story I told you before. It was actually about the same time. Actually, at the time I was working at NASA Ames, and we had a little workshop, and Jim Head came and showed this picture that I've already showed you. They had kind of identified the fact that this landform should be related to glaciers, and at the same time we could see that our model were predicting accumulation of ice exactly there at high obliquity. So it's like this good moment in science where you can jump on your chair and say, Eureka! And it's true. I will believe really the model explained very well its origin, and everything makes sense. You can indeed have glaciers, and this is where you can make glaciers the most easily at high obliquity. The tropics are colder than the pole, and ice accumulate there, and not everywhere. Why is it on the western flanks of these volcanoes? Well, it's because at this season you have, at this period you have most of the time westerlies, air blowing from the west, which is relatively wet, with lots of humidity. And when it meets a mountain like that, it's like in Hawaii, for those of you who are familiar with that, on the lee side, on the wind side, you have uplift, adiabatic cooling, and precipitation. And if you can accumulate up to 1 centimeter per year, and year after year, after 1,000 years, you can have a glacier. And that's the explanation. It's very simple, just like on the Earth. with that, we could continue to explore. Once you have such a model, you can explore lots of configuration, various obliquity, various histories. For instance, we know that when the season of perihelion change, when, for instance, currently the North Pole summer is colder than the South Pole summer. So in some way, the ice is stable at the North Pole. But we know that this can change. The South Pole can be the place where ice is stable. So if you imagine that ice is available at the South Pole, we made simulations. We find that, again, ice will continue to accumulate in the Tarsis area, on the big mountains here on the left. But also, we find that there is a place on eastern Hellas where ice could accumulate. And the reason is that during summer, when the polar cap is really hot and the atmosphere very humid, there is a kind of vortex around the pole, but the Hellas basin here, that you can see the thing here, is creating kind of what we call a stationary wave with a just on the eastern side. One of the specialists for that is Jeff Hollingsworth, who's in the room, who really worked on this problem. And he showed that you can find that there is a water a flux of air, humid air. All the air coming out the polar regions goes onto the eastern side of Hellas. Cool, meet colder air, condense and precipitate in this very specific location. And I have to say that when I discovered that, that was in, again, 2005, something like that, I got this from the model and said, what's that? Because at the time I was not that familiar, at least with this geology, and then looking at the literature, I realized that there were already a huge number of papers focusing on this area, which is very specific, Eastern Hellas, which is full of rock glaciers, moraines, and low-bedded plants characteristic of ice activity. So now we have a new regime, another scenario to explain what is going on there. And I will continue, I will actually, very quickly. You can imagine then, okay, at high obliquity, we understand that ice won't be stable at the pole anymore, will accumulate in the tropics, like for instance, the tropical around the tropical mountains. Then what happened when you go back to low obliquity? Well, we can simulate that, and we discovered that the ice will not go back to the pole, but this time will tend to accumulate around in the mid-latitudes all the way to the pole, at high latitude, to form a kind of mantle, to accumulate very slowly. This is a simulation that was published with my student Benjamin Levra. Actually, he was a postdoc at the time. And in 2004, and we discovered that you assume that there is a glacier available near Tarsis, and you lower the obliquity, the ice becomes unstable, and form this layer very slowly, 1 millimeter per year. And of course, this inspires and it suggested that Mars maybe at the time was looking like that. And this is not connected, this cover of Nature is not connected to a paper, it was connected to a previous paper by Jim Head, who has already suggested that. So already everything makes sense once again. A good model that will predict this behavior. And we could imagine that when the tropical source is exhausted, then the ice in the mid-latitudes become unstable. You can see here in pink that this is the ice subliming, the sublimation rate, and finally, according to our model, will form the polar cap, the northern polar cap as we know it. And when it sublimes, you can imagine that because it's accumulated very slowly, it's full of dust. A part of the ice sublimes, but it leaves the dust behind, form what he calls a lag deposit. We can protect the ice. And that was a scenario that we proposed to explain the observation from Mars Odyssey. This is a little debated. Other people suggest that this ice that is observed by Mars Odyssey and Phoenix is not coming from precipitation, it's coming from diffusion of ice and formation of kind of ice lancers. I won't debate that. We have a workshop this week, and yesterday afternoon we had a hot debate on this subject. It's very fascinating. Big controversy. I could continue, and I will continue once again. One more last example. If you imagine now that you go back from high obliquity to low obliquity, but you take into account something that other team had discovered, the fact that at high obliquity, the wind can be much stronger than today because the seasonal contrasts are very strong. You can expect to have more dust in the system. And if you take into account this dust, there are lots of dust in the atmosphere, which tend to warm the atmosphere. The behavior of the system is different, and we discovered that then, not only you form the mantle at high latitudes, but you tend to accumulate ice in some specific location. You can see here a movie showing the dynamics of this, what happened then. You can see this is ice accumulation rate at a given season. So you can see lots of precipitation on the western flank of the topographic feature at mid-latitudes, and that was also very interesting because that matched very well where lots of glacier, or the last kind of glacier features have been observed, especially the area of the Torinus Monse around 60 degrees east, and that this has been known for a while. And we believe again that we have identified a robust mechanism that would explain why you can make this glacier. Okay, so that's conclusion one for my talk. Thanks to the modeling, we now understand that due to the variation of the rotational orbital parameters, the current mass climate system, you have to change nothing in the assumption. The atmosphere is the same, everything is the same, just change the obliquity, for instance. His system is able to mobilize large amount of water from glacier ice, and until recently, and that will continue in the future. Of course, I have to stress on the fact that lots of issues remain in the model. To be honest, the model was very well designed to simulate present-day Mars, but to simulate this past climate, we're not so sure, because, for instance, until recently, we had been neglecting the radiative effect of water ice clouds. If you do that on the Earth, you're very wrong. I think that if you do that on this high obliquity climate, where you have lots of water vapor and clouds, it's probably wrong as well. So in the past years, we've been working on improving our model, and we're starting to have results. I won't tell you about these results today. Come to the workshop tomorrow if you want to hear that. But it changed a little bit the story. With the time left, I would like to move on to a third subject, the last part of my talk, which is not present-day Mars, not recent Mars, Mars in the past million years, but the question is, can we simulate also with the same kind of tools the climate of Mars 4 billion years ago? Early Mars, this planet Mars, where lots of geological, mineralogical observations have suggested that it was a very different planet than today's, with lots of water vapor involved, you know, the valley network with the dry riverbed, lots of mineralogy with especially the detection of clays in deltas and so on. You all know this story. Early Mars was a different planet than what it was after that. Mars before 3.5 billion years ago was completely different than after 3 billion years ago. So what happened there? It's an enigma from many aspects. There are various aspects of this enigma. So we have more and more clues from this mineralogy and geomorphology that suggest that on early Mars, liquid water was probably flowing and acting, but key question remains. We don't know if the conditions that were suitable for liquid water were episodic or stable on a longer time scale. There is a lot of debate in the community. We don't even know if it was really something which was like the Earth with precipitation, or if lots of this, the observations that we have can be explained with just, for instance, hydrothermalism. What we know for sure is that Mars was different. So why was it different? If you want to model that, for instance, we have to take into account what could have been different, and what was different then could be, for instance, the fact that the sun was different. And as you can see on this picture, the sun was different indeed. It was younger, and younger was not good for the climate. I mean, if you want to have liquid water, because it was, as most of you know, it was fainter because of its the way the thermonuclear fusion works. You have less density inside the sun, so it was less active. Less energy, so it was fainter, about 25% fainter 3.8 or 4 billion years ago. Then you can take into account the fact that maybe the geothermal heat flux was stronger. That will help to have hydrothermology and things like that. Maybe, you know that between 3.9 and 3.8 years ago, we have the late heavy bombardments. Mars was a planet with lots of impacts from asteroids and planetesimal, like the Earth, and maybe that played a role in this story. And finally, maybe the atmosphere was different. Most likely it was different. In billions of years, probably evolved. So there have been a lot of work suggesting that in fact the atmosphere was probably the atmosphere of CO2, like today, but probably much thicker. And there have been a lot of papers, it's been published, suggesting that early Mars was different, not really because of the bombardment or something like that, but because the atmosphere was thicker, the greenhouse effect was stronger. That could explain the story. And to start with, in the past years, we have been working on trying to simulate early Mars, and what I call early Mars is just a Mars-like planet on which we assume a thicker atmosphere to explore a range of pressure from 0.1 bar up to, or even less, up to 2 bar or more. And we take into account also the sun that was fainter. It's a very interesting topic if you want the story of science, because there have been lots of papers published on this exact problem. What could be the climate on the Mars-like planet with a thicker atmosphere and a faint sun? You can see a list of papers here, starting even before like 87 and so on. It's interesting because you can, if you read them, each of these papers was written to demonstrate that the one before was wrong. And it was actually true. And today I'm proud to continue this tradition and, and to actually indeed show you that if you use a 3D model and improve the spectroscopy, I will show you, you can have better different results, and in fact find very similar results. Once again, we're using one of our version of our global climate model for early Mars. You have to modify lots of things. In particular, our challenge is the radiative transfer in a thick atmosphere, with possibly you will see CO2 ice clouds. But a real challenge was the spectroscopy of CO2 with a high pressure, and in particular a process which is the CO2-CO2 collision-induced absorption, for those of you who are familiar. And working on what was available, we discovered that all the previous work had been using, including mine, to be honest, had been using a parameterization for this CO2 collision-induced absorption, which was wrong and significantly overestimating the greenhouse effect. So we have corrected that, and we now believe that we have a more realistic greenhouse effect of CO2. We also include again microphysics and some physics for the CO2 ice clouds. Let me show you, for instance, the kind of CO2 ice cloud activity we have. You can see here a movie where you see a different kind of CO2 ice cloud. Some are, so this is a map with a CO2 ice cloud mass. Some are connected to topography, others are related to weather, traveling weather pattern, and so on. What's interesting with CO2 ice clouds is that they are very different from water ice clouds. To the eye, they will look the same. They are wide, they scatter the solar radiation, but in the thermal infrared, they are, unlike water ice cloud, for instance, on the Earth, they not only, they don't really absorb the infrared radiation, they actually can scatter it. And this scattering, I published a paper with Ray Pierre some time ago about that. This scattering is a very efficient way to create a greenhouse effect. We just reflect the thermal infrared radiation coming from the surface, and it's even more efficient in absorbing and re-emitting. So the CO2 ice cloud were actually suggested to explain why early Mars could have been so warm. So we put that in a model, tried to explore all the possible spectroscopy, and in fact found that they help. It's not sufficient. And in fact, I show you the results. We find, this is an example, we explored many kind of parameters, obliquity, pressure, everything you can imagine, microphysical parameters. This is a typical results we have for present-day obliquity. We find that depending on the pressure, we can't really warm the planet. You can see here, so if you compare to a very low pressure, the CO2 gas can have a greenhouse effect up to typically 20 Kelvin. You can see here the solid line shows the results in taking into account the greenhouse effect of CO2 ice clouds. It adds maybe 15 Kelvin of greenhouse effect, but we are still just above 230 Kelvin, minus 50 degrees Celsius, very cold planet. We are very far from all the previous results. We could suggest sometime average temperature above 0 degrees Celsius. And we have tried every model parameters to challenge, to see if we could warm the planet. It's not easy. If you look at the details, this is a map of the global mean, not global, but annual mean surface temperature that you can have for 2 examples of pressure. And you can see it's very cold, actually. Transform, you can see the kelvins into Celsius to facilitate the comparison with the freezing point. And we are very far from the freezing point. One thing you can notice which is interesting, especially if you're familiar with Mars, is that unlike on present-day Mars, the temperature start to be with some pressure, start to be sensitive with altitude, with topography. you can see that in the lower plains here in the north, you have the higher temperature than in the high plateau on the south. That's not surprising. On the Earth, it's colder in the mountains than in the plain. On present-day Mars, it's not the case. So you have a change of regime where you really start to have cold place in the mountains. So you could say, well, if it's that's average temperature, but you know, in Siberia you have places where the annual mean temperature is minus 20 degrees Celsius, and still you can have lakes and rivers. What the real criterion for the activity is the diurnal mean temperature in summer typically. So you can look at the max daily mean temperature, and there again, when you look at that, you can see that it's a little warmer than the average temperature, but you cannot really warm and have lakes and rivers. Then you could say, well, maybe it's like in the dry valley in Antarctica. Some dry valley in Antarctica has even the maximum summer diurnal mean temperature is below 0 degrees Celsius, but from time to time in summer, in the afternoon, you can melt a little bit of ice, and that's enough to have lake-covered glaciers with a biological activity. So you can look at the maximum temperature, which will be a criterion. You find that in that case, you can have temperature above 0 degrees Celsius, but in reality, if you take into account the fact that the ice has a higher albedo and a higher thermal inertia, that's, for instance, here, maximum temperature assuming ice on the surface, it's very difficult to melt ice. So we have a really cold planet. So how can we warm the planet? Maybe with additional greenhouse gases. We're working on that. It doesn't work very well, to be honest, but I won't show you this detail. What I want to show you before ending is other results. What happened on this relatively cold planet if we add a water cycle. So we included a full water cycle with that's really a work which was performed by Robin Woodworth, who was postdoc in our institute. And if you add a water cycle with what the effect of water vapor, the clouds, all the transport, microphysics, everything, then you can really better understand what could have happened on this planet. A side point is the fact that water vapor is a greenhouse gas. It helps a little bit to warm the planet, but you can see here on this plot, this is the mean surface temperature, the question of pressure, assuming 100% humidity and no clouds, maximum greenhouse effect of water vapor, and still you only warm the planet by a few Kelvin, so it doesn't work to warm the planet. Nevertheless, now we have a complex system with CO2 ice clouds above water ice clouds. We can simulate precipitation. In practice, this is snow precipitation for various seasons and so on. And we can explore what happens. There are so many parameters start to be complicated because you don't know where to assume the ice is at the origin. When I model present-day Mars, it's easy. I start with ice on the North Pole and I can simulate what happened. In that case, I don't know where the ice is stable. And in fact, to better understand that, we have designed a scheme in a model where we simulate a water cycle starting with ice in some location, and every 2 years we check where the ice is accumulating or where the ice is subliming, and we imagine that we extrapolate that for hundreds of years and we start again. So in the end, we remove the ice where it's not stable, and we find where the ice is stable in the end. And when we do that, this is an example of 0.4 bars, we find that, you may say it's logical, that the ice, unlike on present-day Mars, tends to go not only to the pole when the obliquity is low enough, but tends to accumulate in the highlands, on the mountains. And that's interesting. It's very different on present-day Mars. Maybe that's a clue on what happened then on early Mars. This is another simulation with 2 bars. This is high obliquity. We removed Tarsus because more than 4 billion years ago, Tarsus was not there. And we can explore where the ice would have accumulated. What could happen? That's background for all people who want to study what could have happened then. Okay, I won't show you that too much. Almost there. Could this icy Mars be early Mars? Could we imagine that everything that we observe in the geological records of that time could be explained by the fact that you have ice accumulating in the islands? Well, why not? The thing is that early Mars was different, and with a thicker atmosphere was different than today, Because first, ice tends to accumulate in the highlands. And second, of course, with higher pressure, it's much easier to have liquid water. So if you warm the ice because of a volcanic eruption or an impact, you can really flow. So maybe we can explore now a new paradigm. Maybe a cold glacier-rich early Mars with episodic flowing water, which will be related, for instance, for volcanic activity, geothermal heating below the glaciers, basal melting and flow below the glaciers and so on. Episodically impacts into the ice that will create melting and flow. Very big impacts could create actually climate change. That's another story I won't detail. That's the work by Brian Toon and his team. And maybe impacts or volcanic will melt the water. Water will flow down into the lowlands, the plains. And what's interesting with this model, we have identified something which was a big question. A recharge process. Just the fact that ice tends to accumulate in the mountains, an obvious fact. Now that we model it, we can tell, in fact, it's very easily, you melt the water, it flows down, but once it's in the plain, it's not stable. It sublimes and go back, reaccumulate from glaciers in the highlands. That's the story for early Mars, and I will thank you. We'll take questions. Thank you.
Do we have questions for our speaker?
I'm not quite sure if I got this, but what's the maximum temperature that you could achieve on your simulations?
For early Mars? Mm-hmm. The maximum temperature at a given point on summer in the afternoon at 2 p.m.
Right.
It can be 15 degrees Celsius. No question. To be honest, on present-day Mars, you can have surface temperature up to 25 degrees or 20 degrees Celsius, but it's completely dry. So you have to see if you have high temperature and water available. That's the real difficulty.
So the maximum temperature is on the best of your simulations, but how far could you go up? 15, but 20 if you want. It's 20 degrees centigrade?
Yes, but for a few minutes in the afternoon.
Okay. So that would be high enough, obviously, to melt water. It's above zero.
Yes and no. First, in fact, I have thoughts about that. We have a paper in Mid-latitudes by the first author is Robin Woodworth, and there is plots about the fact that indeed, in some simulation, we can melt a little bit of water. There's two caveats. The first is that we don't melt a lot, really a little bit of water. But nevertheless, we do melt. In other words, we can reach above 0 degrees Celsius temperature in area where ice will be stable. It's not the case on present-day Mars, it's the case there. That's a good point. But we don't, it's a few droplets. The other thing is that in these simulations, we don't completely take into account the fact that the ice has this high albedo, kind of high thermal inertia, and we're not so sure that it will really happen. Let's put that another way. If you assume that you have big glaciers, for sure it won't melt because it won't warm in the afternoon. If you are at the edge of a snowpack with warm air coming from the rock around, then you will melt.
Okay, and let's see, what's the maximum amount of geothermal energy that one could conjure up, knowing what we know?
I don't know the number, but what I know for sure is that the geothermal, right now it's pretty low. In the past it was higher, especially very early in the history. Right. The heat flux is really doing like that in log scale. But the thing is that in terms of surface temperature, the geothermal heat flux have very little impact on the surface temperature. It's even if you put a few watts, in the end compared to the other flux, it's not very important. Where the geothermal heat flux is very important is when you compute subsurface temperature. Yeah? Then you have a strong gradient, and then it plays a role. So most likely on early Mars, the geothermal heat flux was higher, and for instance, the 0 degrees Celsius isotherm, instead of being a few kilometers below the surface on present-day Mars, maybe was 100 meters below the surface. And that includes in glaciers. So maybe you had thick glaciers, for sure you will have lots of basal melting and lots of liquid water activity below the glaciers.
But you could sort of set an upper limit just by knowing that obviously there are volcanoes there. And the second thing is that the Valles Marineris was an initial attempt at plate tectonics. You can sort of use those two sets of phenomena to sort of set an upper limit on the geothermal capacity of the planet, I suppose.
I'm not sure it's plate tectonic, but what I'm sure is that it's not exactly my specialty. But I'm sure there are people working on that.
Okay.
Thanks. Other questions?
I've got two questions. The first, I wasn't clear on getting up to 2 bar of CO2. Was it the obliquity that brought about that
It's a very good
seems to be a
question.
very large pressure. I don't quite...
It's exactly, well, it used, we're talking about Mars 4 billion years ago.
Yeah.
And the initial story that people will tell in the early papers in the 80s or even early 90s was that if you compare the inventory of CO2 on Venus or on the Earth, where you have 90, 60 bars. If you scale that to Mars, you can imagine that Mars started with about 10 bars of CO2. So you can imagine that these 10 bars were available, at least a few bars, to make the atmosphere. And that's the rationale that was in many papers, and it's still true. You can still speculate that. Now, I think it's a very wild speculation because most of the recent work show that there are problems with that. Because we now believe that, so in our model, we continue to play with this story to imagine that we could have 2 bars of CO2. But in reality, I personally believe it's probably not the case. And the reason is the following. First, every model shows that with such a low gravity, the early Mars that could have been outgassed initially was blown away by a very high extreme UV flux. The thermosphere was very hot and escape was very efficient very early, 4.3 billion years ago. Then there could have been a later atmosphere, hot gas from the mantle. And for instance, there are speculation that the rising of Tarsis Bulge, lots of lava, released up to maybe a bar of CO2. But it's controversial. That's a paper, for instance, by Roger Phillips, which is very well known, this paper. Recent work has shown that he overestimated the capacity of the mantle to own CO2. In fact, probably the hot gas was much less than that. Okay, but now, once you have this CO2, you have to get rid of it. And again, there are lots of debate whether there are escape processes able to get rid of 2 bar in the atmosphere. And there again, it's a complete scientific field. You have a mission named MAVEN, which is designed to better understand if you can have escape processes able to remove 2 bars or not. Right now, the recent work suggests no, the escape. You need non-thermal escape, it's very complex, to remove large amount. The estimation is that at most, typically, 500, 0.5 bar, and 0.5 bar. But you can speculate that, well, maybe some of this atmosphere is now in carbonate. Carbonate used to be in fashion, then Omega on Mars Express and Prism initially did not discover much carbonate, so carbonate is not, but now we're starting to discover carbonate again, so there is another story in carbonate. So your question drives me to many scientific fields which are...
Well, there are a lot of oxides, and so carbonates are certainly reasonable, I guess, isn't that right?
It's true, but the story is more complex than that.
Okay, quick question number 2. With regard to liquid water at 2 bar of CO2, isn't it the case, though, that the phase of water is dependent upon its partial pressure, not the total pressure? So how can you suggest that there would be liquid water
on
Mars?
Just like on the Earth. There is liquid water on the Earth. It's not stable most of the time. If I put a glass of water here, the partial pressure of water will be lower than and it will evaporate, but slowly.
Oh, so it's a transient. Oh, it's a transient, very transient.
Just like on the Earth.
Oh, I see.
But you have area where it's stable. You have to accumulate somewhere, so it will be just like on the Earth, except that it will be much colder. So you will if you have a glacier and you form, I don't know, liquid water through volcanic activity, then you flow, but ultimately you freeze.
Other questions?
I think this.
Sorry.
I think my question has been partially answered, but about 30 years ago, they were talking about a bimodal, high pressure, low pressure. And I think maybe you've already answered that question. But was it a freezing CO2? Non-freezing CO2?
Oh, I see what you mean. Yes, it used to be something which was discussed. There were two reasons for that. So the idea is that when you, on present-day Mars, you have only a few millibars of CO2. When you increase the obliquity, you could release a lot of CO2 and have a thicker atmosphere. There were two reasons. The first was the idea that there could be a lot of CO2 stored in the polar regions, and indeed, when you increase the obliquity, this CO2 ice, you have a little bit of CO2 ice permanently frozen right now at the South Pole. If you increase the obliquity, it sublimes. At some point, we didn't know how much there will be. We used to think some people speculated it could be a lot, a few hundreds of millibars. Then we realized it's not much. In 2004, it was really identified that it's only less than it's a few tenths of percent of the current atmosphere. Then last year, thanks to a radar, SHARAD, on Mars Frequency Orbiter, we have discovered a reservoir of CO2 below another reservoir of CO2. Now we know that you have about the equivalent of the current Mars atmosphere frozen at the South Pole, 5 millibars of CO2 there. But that's only 5 millibars. The only reason why people were speculating that at high obliquity the pressure could increase was the idea that when you would warm the high latitudes, and in the subsurface down to a few tens or hundreds of meters, and if you warm the pores, a regolith which is in contact with the atmosphere, there you have CO2 which is adsorbed in the surface of the pores. If you warm it a little bit, you dissolve CO2. And estimations were suggesting that you could dissolve a significant amount of CO2. But very quickly, most recent papers suggest now that at most you have also a few millibars of CO2. So this is a real story. Now we know that the pressure will increase when you increase the obliquity, but only by a few millibars.
Question over here. Jumping ahead to the Amazonian, your model, when you increase the obliquity above 40 or 45, you got ice depositing near Tharsis, and then we see these glacial deposits there. So I'm wondering how long the obliquity needs to remain that high in order to form the glacial deposits that we see. The features looked pretty long, so it looked like the ice was flowing for some time.
That's a good question. The obliquity has a kind of oscillation with a 20-degree amplitude. Remember the plot I showed initially, with a period of a few like 60 million years, 60,000 years, sorry. And let me find the plot. Where it is? It's there. Here it is. And then, in addition to that, so you always have this oscillation, except when you have nodes and so on. The world expert of that, Jacques Lascar, you will give a talk about that tomorrow at AIMS. But and you can see also that sometimes it jumps. For instance, and in that case, it jumps from oscillating between 15 and 35 to oscillating between 25 and 45 degrees, and it can jump even higher. So there's two answers. Most of the time, you go to high obliquity, maybe you form glaciers, I don't know, and then a few tens of thousands of years later, you stop doing that and you go the other way and so on. But maybe sometime you went all the way to high obliquity and you stayed there for a while between 35 and 55, something like that. And in that case, you have a permanent regime. But to be honest, what will limit the growth of the glacier is not the duration of the high obliquity phase. What will limit the growth of the glacier is the total inventory of water. If you remove the entire polar cap at the North Pole right now, you will form nice glacier and that's it. Not much. You won't cover the entire region. So what is really controlling the geomorphology right now is the fact that it's limited by the amount of ice which is in the system.
Do a response over here.
It's a question is a perfect follow-on to what you just said, and that is the inventory of water. Norm Sleep calculated that just the fracture space that's now been generated by the cooling of the crust in the last 3 to 4 billion years could easily hide 500 meters equivalent of water. So a lot of the water that formed some of these early features is probably now stored in the subsurface. And so the question then is, if you increase the inventory of water, which pretty much addresses the comment you just made, what effect would that have? And of course, the other little question I'd like is above 45 degree obliquity. You went up to 45, but what about models that go to even higher obliquities? So 2 questions.
Okay, if you increase the inventory, we didn't do simulations. The reason is that when we do climate simulations, we don't really make any assumption on the total amount of we just simulate a regime with for instance, an infinite inventory at the pole, and it starts to create glaciers. We have done some studies about the formation and the inventory. That's a paper by Benjamin Levra in 2007. And there, the goal was to simulate, for instance, the building of the northern polar caps. And when we do so, it's true that we know that the total inventory makes a polar cap which is a few 3,000 meters thick and so on. If you increase that a lot, honestly, I don't think it will change that much the system, because ice will accumulate, you form glaciers, they will flow. If they're very thick, they will be bigger, but I don't think it will be a big change. The second question was what happened at very, very high obliquity. Well, in fact, this is just a model. Okay? In reality, I don't know, but in the model, it's a little bit of the same. The northern pole is even more unstable, and you form the glacier. I think in reality, what will happen if you go, for instance, through a high obliquity, 45, 50, and so on, up to, I don't know, 60, then when you reach 60, it's been a long time since there's nothing at the pole, the glacier are in the tropics, and all the water cycle is around there, and that's kind of stable. The time scale of this ice moving is somewhere faster than the evolution of million years. It's a few thousands of years, I think, or tens of thousands.
With regards to future research in this field, if you were able to design your own mission to Mars, what piece of information would you want it to collect, or what would you want it to do if you could design your mission?
Good question. That's a typical question I ask to students when they defend their PhD. So my answer, well, you can see there are different topics here. One big mystery, enigma, and challenge is this: the origin of this ice mantle in the high latitudes. Honestly, there is a real controversy and debate about how you make that. So it will be interesting to have a mission that will help, and you can measure in more detail the ice, isotopes. You can do a lot of measurements about that. But to be honest, I'm not sure it will be the priority for most of you, and including me. We also have to understand what happened, the bigger thing, what happened on Mars 4 billion years ago, or 3.5 billion years ago, early Mars. Because as you can tell, even though we have lots of literature, lots of studies, we still don't know if it was episodic or not, really water, underground, the origin of minerals, the clays, are they made through vegetation, or it's a debate. And so a big rover going to a good crater, that's a good idea, so that's MSL this summer. And then the next steps will be, I think will be to continue that, because all Mars is really a big planet, and you have lots of different epochs stored in the geological report. So radar could really help, more precise radar could really help to better identify the story of the ice, and maybe help also for early Mars. So I'm afraid I have only obvious suggestion. Actually, it was on the Decadal survey panel, so I had the opportunity to give my ideas. But on the other hand, I realize that there is not enough money, so I have to stay realistic.
Great, I think we'll close off questioning there, but I'd like to thank our speaker one more time.